Good morning, good afternoon, good evening. Welcome to Hands on SAP Dev, and you're hosted by today me, DJ Q Macro, on the SAP Devs channel. So very exciting. I'm sitting here. I've got the door open because it's quite warm, so it's a bit of an experiment. And just as I went live, a massive fly just flew in. It's been buzzing around. I think it's just flown out again, so hopefully that's okay. Yes, so welcome and thank you for joining. Friday, 31st of July. I've got my coffee. This was the thing that was missing in the photo that I tweeted. So yeah, let me know how you're doing. Let me know how you're feeling today, whether you're set up for success, whether you're set up for a little bit of a brain exercise with what we've got to do today, which is building a recursive version of Reduce. Jodelle, good morning. Christian, good morning to you as well. It's great to have you all on board. So yeah, let's get started. I've got my coffee. I've just brewed it. In fact, I need to go to the Heart and Graft roastery down the road to get some more coffee. Well, that's good. That is good. That is good. So let me switch to the main scene straight away. In fact, funnily enough, this particular scene that you're looking at right now, I did have the idea. Now we've got Samuel. Samuel, good morning. Good morning to you, and thank you very much for the comment you made on the video from Wednesday. Really appreciate it. I'm really pleased that we've moved now to the SAP Devs channel. In fact, let me just show you what the SAP Devs channel looks like. So if you haven't subscribed already to the SAP Developers channel, SAP Devs channel, there's that fly. You see it? It's really loud. Maybe it's going to be picked up. Maybe it's going to hit the Yeti microphone and deafen you all. Vladimir, good morning. Good morning. So yes, please capire. Yes, was that? So I need to know how to pronounce it as well. So Samuel. So it's from Italy. Yes, thank you very much indeed. So yeah, this is SAP Developers channel. Make sure you're subscribed to this, and that means then you'll catch all of the upcoming episodes of all my colleagues. Tom and Rich and Kevin and Max and other folks as well. So there we go. Andrew, good evening to you, sir. Good evening. I hope you're well. I hope you're well. How's the coffee going? I've got my coffee here. So, on Wednesday was my first venture, my first episode doing Hands on SAP Dev on the SAP Developers channel. And I had the awesome Ivona Hahn as a guest. We had a few problems at the start of the live stream, and those were all my fault. As I said to Ivona at the start as well, anything that goes wrong is my fault, and it was. But if you haven't seen that, check that out. So go to the SAP Devs channel. Buongiorno, Max, buongiorno. However you spell it, yes. And check that out. And also, I've got, here's my little thing here. If you have not already started following Ivona on Twitter, she puts out stuff relating to CAP. What an awesome person Ivona is. So yeah, check out Ivona's tweets there. What else have I got to share? Oh yes, talking of Twitter, I thought it was quite a nice lead in to the subject of today. So John Patterson, down under somewhere. I don't know where John is exactly. I sometimes have the feeling he's in Tasmania, but maybe that's just Matt. I'm not sure. Hey Renita, good afternoon. Good afternoon to you, and welcome. Thank you for joining. Thank you for joining. I hope you're okay. John, in a conversation with various people, including Glenn and Jacek, about ABAP and everything, and he was asking about styles, preferred styles for closing brackets, and Jason as well. And anyway, John said, I never like changing, blah, blah, blah. Nowadays, I tend to write FP, functional programming, or functionally, I suppose, and look to avoid shared state mutations and side effects where possible. So I think that was a really good sort of thing to think about this morning, because that's what I'm trying to do as well. And of course, the subject of today, we're talking about Reduce, we're talking about a recursive definition of Reduce. I've talked about functional programming before. I think it's really nice from a pleasantry perspective to learn about this stuff, but it's also useful. It helps our brains, right? Pierre, hello, Pierre, welcome. Bienvenue, as they say down in Lyon. And talking of, expanding one's brain from a programming language perspective, a guest that we're gonna have on soon on Hands on SAP Dev, David Kuntz, who also spoke at SAP Online Track. Did he speak at Online Track? He definitely spoke at Recap. He was in my session at Online Track. Anyway, David's a wonderful person, works in the CAP team as well, and he has this blog post on Rust, which is a fairly new language. And again, it's all about, I think learning new languages really helps me, speaking for myself, to understand the languages that I'm using currently. And he points to 3 papers here as well: Edgar Dijkstra, Alan Kay, father of Smalltalk, and therefore possibly arguably father of object orientation as well, and of course John McCarthy and Lisp, who I mentioned in my talk as well. So check that blog post out and start following. I've not even liked it. Start following David on the SAP community. So that's that, and I think that's it. Yeah. So I've got some slides I want to show you from the functional programming talk that I did at SAP Online Track, which was an awesome event, and we're going to use just a little bit of material from those slides to sort of gently guide ourselves into building this recursive version of Reduce. I'm just going to check over here. I think we're okay. Stream health is looking good. Let me just minimize, make that a bit smaller. What am I doing? Yeah, excellent condition. Very good. Excellent condition. Excellent. Okay, so let's close that and go to, this is where we left off last time, right? I wanted to show you, I'll just pause that video. I wanted to show you where we left off last time. This is the video, if you haven't seen this already, I would recommend you look at this as well. This is the video from last Friday on my channel, the last video on Hands on SAP Dev I did on my channel. And this is the definition of reduce that we ended up with, okay? So we went through a series of, exercises and ended up building a reduce function that was, and I was calling it like a Ramda style function signature, i.e. a normal function, not like a prototype reduce function attached to the array object, right? So the reduce function takes a function, takes an accumulator, like a starting value, and takes an array and uses a for loop in that particular version of reduce, uses a for loop to go and iterate over the elements of the array and produce the result, produce the reduced value, depending on what that function is, and also what the starting accumulator was as well. So what we're going to do is we're going to define reduce again, but using recursion. Now, before we do that though, and also, by the way, I think it was in that episode that I realized that one thing I should have, COBOL, oh yes, one thing I should have is a biscuit, because I choked on the coffee because I think it didn't have a biscuit. That was the reason I decided. Just before I look at the comments here, I'm just going to move to here. I've got this blank page, which of course means that I've got over here a really nice environment in which we can program together, which of course is the developer tools, which I like. And all I've got in here, I've got that function reduce, which we had from last week. So we can say, for example, add equals, let's have a little reduce the function add equals, takes A and B and produces A plus B. And now we can say reduce, oh no, let's have nums as well. Nums equals 1, 2, 3, 4, 5, 6. So now we can say reduce using add function starting with the accumulator of 0 nums. 1 plus 2 plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21. Yes, I suddenly panicked. I'm thinking 21, is that right? But of course, I think the nums last time I only went from 1 to 5. So there we go. So far so good. So, speaking of languages, Andrew says, do we know who the parents of ABAP were and what language influenced early ABAP? Well, I think Vladimir, I think you're right there. A COBOL was definitely an influence. PL1, well, possibly had an influence, but I think at the time, PL1 was around at the same time as ABAP. When PL1 was, I was programming in PL1 when ABAP came on the scene. Although, yeah, so Vladimir, I think you're right. Plus, you've got to remember that ABAP started out just as a report writing language. It had very, very few keywords, and it was all about building sort of list reports with sort of subsections and subtotals and so on. And that was it. That was all ABAP was. So ABAP as a language started very small, very small. There was no database, direct database access. Of course, there was the concept of logical databases, and there were these so-called events. I know we've talked about this before. I'm still going to call them events. Basically, there was the ABAP code that you wrote rode upon the back of a logical database read program that spat out events every time it read a certain segment. Okay, and then you could react, like collect or append to a, effectively like not an internal table, but that sort of thing. So it grew very, very slowly but surely. Yeah, so there we go. Yeah, ABAP 4, Andrew, ABAP 4. In fact, the ABAP I started with, which was very, very early. It was before ABAP 4, which was called ABAP, and there was an ABAP 3 as well. Anyway, we're getting distracted, but that was a good distraction. All distractions are good, I suppose. This conversation is good. So yeah, let me know your thoughts on what else you might think has influenced ABAP. What do you think influenced JavaScript? So Samuel, is that Samueli? Am I pronouncing your name right, Samueli? I'm not sure what you mean with bird in R2, but yeah, this was it. I'm thinking of R2 when I was first started programming on SAP. In fact, when I first started SAP developing with SAP, it was on R2 and it was in assembler because there was no ABAP. Anyway, so let's get back to where we wanted to go, which was to think about this. Now, the final thing that I had in my list of things to look at was the set of slides that I created for this talk, functional programming talk. Now, where was it? Because I want to sort of introduce us slowly to recursion and then slowly to pattern matching and the whole beautiful concept introduced very nicely by, can anybody tell me who this person is on the screen with his tie-dye t-shirts and my favorite phrase of his, which is X over X's, and the concept of head and tail, right? Which is fundamental within Lisp and in many other functional programming languages and list processing languages. So let's start out by sort of implementing. Let me just set the there we go, implementing. And if I do that as well, make that a little bit bigger, we can see both things. That was my car, by the way. That's my 1973 Chevrolet Caprice. My other car is a Cuda. Anybody get that joke? Oh, pronunciation is okay. Pronunciation is okay. Right, so there we go. So let's start out by sort of stretching our fingers a little bit. What time is it? Yeah, we've got plenty of time. Stretch our fingers a little bit. And thinking about recursion, first of all. Let's do a little bit of recursion, really small bit. And then we'll start thinking about pattern matching and X and X's, head and tail of lists, because we're going to be using that function and that concept rather to build our recursive reduce. We're going to use a really cool feature of ECMAScript 2015, which is ES6. So it's quite an old version, but it's still modern to us, right? Which is the spread stroke rest operator. So if you know what the spread stroke rest operator looks like in JavaScript, put it in the comments here, put it in the chat. So just so you know, I don't know whether you saw the picture on Twitter I tweeted. I've got a big screen in front of me, which is where I'm doing my doing. I've got the live streaming YouTube studio with the chat as well, which is over here. This is why I'm looking over here. The microphone's over here, right? So, but it's a good microphone, so hopefully everything's okay. Also, I've got this ring light now, which maybe is making my head a bit shiny, but that's okay. But I keep getting distracted. I keep looking at it. I don't know why. Anyway, stop being meta. Why don't we implement this factorial function in JavaScript? I should be able to see that. Yes. So factorial, factorial of 5 is 1 times 2 times 3 times 4 times 5, for example. So we're going to implement that, and it's a perfect example. Really baby steps to implement something using recursion. So that's in Lisp. So we're going to write it in JavaScript. So factorial equals takes n, for example, and it's well, let's do it sort of in a block so we can see it. We're not going to try and do it all on one line. So let's do it in a block first of all. So if n is 1, okay, then we're going to return n or 1. I mean, return 1. We could return n as well. That's a little bit more philosophical, right? But we'll return 1. Okay, that's like the base case. When you're writing factorial, when you're writing recursive functions, you've got to make sure you sort of, are able to escape out of this never-ending self-calling loop, right? And it's called the base case. This is the base case. I'm not going to return a call to myself. In this case, I'm going to return 1. Okay. Otherwise, I'm going to return n, whatever n is, multiplied by, as you can see here, this is like prefix notation, multiplication function, right, with n multiplied by the factorial of n minus 1. So n times factorial n minus 1. So here we've got a reference to the factorial function, which is itself. So this is a self-referential thing. Okay, so that's a recursive definition. Okay, so if we say, for example, factorial of 3, 1 times 2 times 3 is 6. Let's do, because 1 plus 2 plus 3 is 6 as well. It's quite weird. So let's do a factorial of 4. 1 times 2 times 3 times 4 is 24, right? Factorial of 4 is 24. So what's happening is that we're saying, okay, well, factorial of 4 is n 1? No. Okay, so we're going to return 4 times the factorial of 3. Okay, so it's like, let's just do it that. And then factorial of 3 is 3 1? No. Okay, well, it's factorial of 3 times factorial of 2. So why don't we actually do this? We'll say here, if n equals 1, let's write it again. Factorial n, if n equals 1, then we'll say console.log, just so we can see what's going on, right? We can see the sort of this sort of thing here, right? I want to show this sort of what's going on. Console.log just write a fact. Factorial of 1 is 1, okay? And then we'll return 1. Otherwise, we'll return, well, console.log. We're using these sort of, I can never remember what these are called, like this sort of string interpolation things, string expressions. Are they called string expressions? Yes, it is. So Jodelle, yeah, I've got this ring. So I'm going to, in fact, during this call, this live stream, I'm going to actually alternate through the different colours. Right, so here we go. A slightly different colour. You should let me know which is the colour you prefer. So we'll say factorial of n, right, is n. Oh, sorry. Oop. That's the biggest issue. Factorial equals n. If you go up again, you lose it. It equals. There we go. If n equals 1, then console.log fac of 1 equals 1. Okay, that's the base case. Return 1. Else console.log the factorial of whatever n is, right, equals whatever n is, times, we're still in the string here, times fac of n minus 1, whatever n minus 1 is. There we go. And then we'll say here, same as before, return n times factorial n minus 1. So all we've done is done exactly the same definition, but just console log statements. So if we do the factorial now, let's just that factorial, look at that, and say factorial of 4. Yes, that's what I wanted to show, right? Okay, so the factorial of 4 is 4 times the factorial of 3, and the factorial of 3 is 3 times the factorial of 2, and the factorial of 2 is 2 times the factorial of 1, and the factorial of 1 is 1, base case, boing, and everything gets resolved, 24. So that's basically, you know, a really, really simple, you know, not explanation, but example of some, you know, recursive definition. So, yes, the ring light is pretty cool, Jadel. I resisted it first of all, but it actually allows the camera to pick up a slightly sharper definition somehow. I'm not sure how that works, but anyway, yeah, thank you. Andrew, yes, spread operator, ... It is indeed. So we'll be using that hopefully. Yes, 821. Oh yeah, plenty of time, he says. So that's factorial. Okay, so now any questions on that? Because now we're going to move into from Lisp to Haskell, another functional programming language. Now, we're going to do the same sort of thing. We're going to define another function using recursion, but this time we're going to define it using recursion, but with so-called pattern matching, which is a beautiful thing, right? As you can see here from Haskell. So we're going to define the take function. The take, basically, the take function takes two arguments. It takes, you know, a numeric argument like 2, 1, 2, 3, 4, 5. Yeah, how many things to take, how many elements to take, and it also takes as a second argument an array. So if you say take 2, 1, 2, 3, 4, 5, it'll just give you 1, 2. Give me the first 2 elements of the array. Okay. Now the way this works is that we've got pattern matching. So basically, let's ignore the type signature for now because that's a little bit too whoa. So it says if we get take any underscore, we use underscore in JavaScript. I use underscore in JavaScript to represent you know, an argument that I'm not interested in. Yeah, it's like a convention. So this is saying here, regardless of whatever n is, in fact, let's start this describing it. Take equals n array. Okay, so in terms of JavaScript, this first argument, right, this integer is n. Okay, and the second argument is an array of a's. So whatever n is, I don't care what it is. If we match an empty array with the second argument, then we just to return an empty array. Okay, take just returns, you know, how can you take anything of an empty array? You just give an empty array back, right? There's another pattern to match. Okay, so if that pattern doesn't match, goes on to the next one. Ah, okay, regardless of what's in the array, regardless of what the array is, there's the underscore, I don't care what it is. If the first value, if the value for the first argument is 0, as in if the value of n is 0, then also return an empty array. Take 0 of anything, empty array. Sort of makes sense, right? So why don't we implement those two first? I've just noticed a comment here from Andrew. So the recursiveness is n deep. Yes, it is. Is return n times factorial of n minus 1 equivalent to factorial n minus 1 times n. Yes. Now, that's interesting. Are you picking up on tail recursion? That's something I'm deliberately sort of avoiding talking about because that's a little bit like whoa, for this particular session. But if we want to do another session on tail recursion or tail recursiveness, let's talk about that as well, or let's think about doing that. Put it, Andrew, in fact, put it in the, if you fancy something like that, put it in the comments to this video. I think it's really cool. I'm trying to encourage people to put comments to videos as well as the live chat is brilliant. Live chat is most important, but also continue the conversation after the live stream finishes in the comments. Cool. Okay, 8:24. So yeah, so there's a reason why those two things are different from a implementation or implementability perspective, especially in JavaScript as well. So why don't we implement these first two patterns first here? So if we're saying here, if array.length is 0, which is this one, take empty array is empty array, then we'll return an empty array. Okay, so far so good. Pattern matching, you know. And then the next one is basically if n is 0. If n is 0, when we also, I don't know why, I think there's sort of in Chrome Developer Tools, the command completion thing, there's a dot somehow that appears if you do that quite fast. I'm not sure how or why, but anyway, also return an empty array. Okay, and now we're into this bit here, which is a bit sort of, in fact, I think I put further down in red. Wait, what? What is that? Now, this is where the pattern matching goes up a level, okay, in terms of awesomeness. You were hinting at tail recursiveness. So, oh, Mike Hills, hello there. Why don't you return the array? Well, I suppose we could return the array there, yeah. That would be perfectly fine. That would also work in this. You know, there's different ways of doing it, of course, right? Perl's one of Perl's many phrases. Tim Toady, there's more than one way to do it. Just like in the factorial definition, we could have instead of returning 1, we could have returned n, which would have been 1 anyway, right? So it's just, I think it's a style thing. And this, to me, when I look at this as a code reader, I can see straight away, bang, I'm returning an empty array, rather than, oh, okay, I'm returning array. What's an array at this stage here? So this, to me, makes more sense for other people to read this code. Yes, exactly. This take reminds you of the Rust, Match, and ARMS. Yes, exactly. All these languages, you know, take from each other. I think it's brilliant. So now we say, okay, well, we've not been given an empty array, and we've not been given I want 0. So let's assume we've been given a non-zero value in n and something in the array. So now this beautiful thing here, let me just write that. Can you all see that, by the way, on the slide? I can't make, well, I suppose I could go to the slide itself, couldn't I? Go to that slide, go to there. Let's just do that for a second. There we go. Yeah, perfect. So this is a thing of beauty. X over X's. What that does is it takes the array and says, put into a variable called X the first element of the array, and put into the variable x's the rest. Okay, the tail. Put into X the head of the array, and put into X's the tail of the array. That's what this thing is all about. In Lisp, it's called car and coulda for reasons I went into in the call, which is into the talk, which is this thing here, this venerable IBM mainframe. But anyway, it's called car coulda, it's called head tail, first rest, x's, all same sort of thing, right? So we grab the head and we grab the rest, and then we say, okay, this is take. I want to concatenate the head. So in Haskell, that is concatenate. I want to concatenate whatever's in the head, as in whatever the first element is, with take of 1 less than n of the rest. Okay, same sort of thing. So before we go any further, in fact, let me just close that. In fact, I can close that now. That's not a complete definition, but I've pressed enter so I can remember it and call it back again. Thanks, Mike Hills. Yes, I agree. It is readable. Yes, that's more readable than maybe another way. So let's talk about the spread rest operator. If we have an array, have we got nums here? Yeah, we've got nums. If we say, right, and this is using, well, actually, let's talk about the rest spread operator. I'm sure you can look it up on MDN, but basically it's an operator that does two different things depending on the context. If we say, let's say, yeah, we got nums. If we say console.log nums, what gets logged out is the array nums, because nums is an array. But if we say console.log ... nums, okay, in this context, it's is being used as a spread operator, as in it's spreading things out, it's pulling things out of an array. So that gives us that, which is 1, 2, 3, 4, 5, 6 separate. That's the same as saying console.log 1, 2, 3, 4, 5, 6. Okay, so basically, just think of the spread operator almost like ripping apart. So I'm thinking of like a necklace with some beads on it, and the necklace is the array, and the beads are the elements in the array. And you pull the necklace apart, and all the beads fall separate, right? I don't know why, but anyway, that suddenly came to mind, that idea. So that's the spread operator. But and we're not going to use not going to use these 3 dots in terms of the spread operator. We're going to use it in terms of the rest operator, which is almost like the opposite. So if we have nums there's that fly again. He wants its 5 minutes of fame. I'm assuming it's the same fly. Go away. So if we use ... as the rest operator, let me just write something. Let's do some destructuring. We could say, for example, A, B, C, D, E, and F equals nums. Okay. What that is destructuring. It's like basically saying assign A to be the value of the first element, B to be the second element, C to be the third element, and so on. So now A is 1, B is 2, C is 3, etc. Right? So that's destructuring. Now closely tied to destructuring. So Renita, spread operator is equivalent to iterating over the array using a loop. It is correct. Yes, exactly. So now we can do this destructuring, but in the context of destructuring, we could say, for example, and let's use the head and the tail terms here. We could use why don't we use first and rest? Okay, let's use first and rest first of all. First rest. If we do that first of all, this is wrong, but if we do that first of all, let's see what happens. First comma rest equals nums. So what's in first? 1. What's in rest? 2. Okay, that's just saying, just like the A, B, C, D, E, F, that's like first and rest, 1, 2. But if we say first ... rest, okay, we're using the ... now as the rest operator. That's where the name came from. Get it? First is 1, and don't forget to notice that 1 is a scalar 1. It's not an array with 1 in it. But rest is now the rest. Let me just bring that to the top of the screen. First rest nums. There's first, and there's the rest. Okay, so that's a beautiful way of destructuring an array into a single scalar element being the first one and the rest of the array minus the first one. Okay, so that's what we're going to need. That's what we're going to need to implement the way we want to do it, to implement our recursive definition of reduce. So that's also what we need in JavaScript to implement the equivalent of this. Okay, so let's go back to our half written take function, and I think, did I save it? No. No. There. Okay. So we're in the middle of this, so let's just add some more. Okay. So we've done this pattern, which is there. We've done this pattern, which is there, and now we're going to do this pattern. So we'll do it sort of, longhand. So why don't we say const. And let's now, we used first and rest. Let's use head and tail, because why not, right? Same thing. Doesn't matter what the names are. Head and tail, first and rest, X and X's. What's your preferred options? Let me know in the chat. What's your preferred options? What makes most sense to you? So now what we're going to do is we're going to destructure the contents of the array into the first element that's going to be in head, and the rest of the elements, if there are any, which are going to be in the variable tail, right, or a constant tail, right? And now what we need to do is just do this bit here, which is X concatenated with, colon in Haskell is concatenate, concatenated with a call to take, a call to itself, with one less than n, with x's, with the rest. Okay, so we can say return, let's put head in an empty array. We could say this, for example, x, just to be even more explicit, right? This is really what's happening here with this colon. Concat head, right? And then concat, let me just make this a little bit bigger. Doop, doop, there we go. Concat take n minus 1 rest. Okay, let's try that. Let's run it and see what happens. And then let's just sort of pick it apart a little bit. So Renita, first rest and head, tail sounds great. Yes. Yeah, I like them. I like them both. I usually use head and tail when I'm not using X and X's. X and X's. Anybody? Did anybody say in the comments here? Did anybody recognize who this was? Maybe a little bit small. There, who's that? Who is that? Let me know in the chat who you think it is. X over X's, an absolute genius. I think he's working for Microsoft at the moment. Anyway, so if we say take, we've still got nums, right? We've got nums, which is an array of 1, 2, 3, 4, 5, 6. So we take 2 nums. Oh, so some debugging there. Let's continue that. Pause, return, go back to there. There we go. Okay, don't know what happened there. So let's do that. Yeah, so take 2 of nums. 1, 2. Take 1 of nums. 1. Take 4 of nums. Oh, hold on, that's not right. Take 4 of nums. What's going on? Take 4 of nums. 1, 2, 2, 2. What's happening there? What's going on? What's going on? 1, 2, 2, 2. Take. Ugh. Who can spot the error? I've spotted it already, and it's my fault. It's because I've been talking about head and tail and first and last and head and rest. First and rest. Can you spot what the error is? What the crazy stupid thing that I did? I'm using head and tail, but then I forget to use the word tail here. I'm using rest. I suppose the moral of the story here is to pick a pair of words, head and tail, and stick to them. There we go. There, that's better. Take 3 of nums, take 4 of nums, take 1 of nums, and so on. So do we understand now what's going on here? Now we could write this slightly differently. Let's just modify that. Really, a shorter way of doing that would be to do this, wouldn't it? Okay, because that's what we're doing here. We're basically saying take an empty array, put head in it, and then concatenate the rest minus 1. Tail. Yes, exactly. Shaban, hello and welcome. And yes, exactly, tail. Andrew, head and tail go together well. First and rest is slightly dissonant for me. First is a number and the rest is, well, whatever's left over. Yes, that makes sense as well. Okay, so now, where does that leave us? It leaves us with a general sense of pattern matching, hopefully, and a general idea as to how we can split an array into its first element and then the rest of the elements. And we can also see, hopefully, now how we can use recursion to achieve something. And again, don't forget, remember to replace rest with tail. Yes. Thank you, Michaels. Yes, brilliant. Did I press enter there? Yes. Fantastic. What a superstar. Thank you, Michaels. Tail. Oop. There we go. Perfect. I could say I was just testing to see if you were awake there, but no. Well, good spot. Good spot. I hadn't spotted that. Okay. So now let's go back to our reduce definition. Because armed with this idea that we can do a bit of recursion, and armed with the idea that in recursion we can use destructuring to grab the head of an element, the head element of an array and the rest of the elements of the array, and then use that to say, well, chop, 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 chop. Let's try and write our reduce function using those techniques. Have some more coffee. Are we ready? Okay, so now let's call it reduce. Let's just overwrite this definition, right? Reduce equals, and it's going to be the same signature. It takes a function, it takes an accumulator, right? Same as before, but instead of just saying, you know, let's take the array, let's already do some destructuring. What did we decide to use? I can't remember. Head and tail? First and rest? Head and tail. Head and tail. Let's use head and tail. Head, and use the rest operator to grab the tail. Okay, so that already, you know, is working in our favor, i.e., when the reduce function is called with the actual reducer function in Fn, with the starting value, as in the accumulator, that's going to be the accumulator, and with an array, we're already splitting that array up into the first element and the rest of the elements. And they're going to be in head and tail. Now, let's do this as a block, right? And we want, first of all, to do the base case. Because we're doing this recursive, we need a base case to sort of escape, to pop up, to sort of to bottom out, as it were, and go bom, 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 all the way back up the stack again. Notice I said stack there, Andrew. So if the base case is basically if we haven't got a head anymore, yeah, if head is undefined, you know, basically if we're given an array with nothing in it, right? Because don't forget, we're going to be reducing over an array, and that array in the recursive calls are going to get smaller and smaller and smaller. Eventually, we're going to get an empty array, and of course, the head of an empty array. In fact, let's do that now. Let's copy that into my buffer. Did I copy that? Yep. If we say, let's in fact, yeah, in the command line, let's use first and rest, and then let's go ahead. Yeah. So, oh no, let's do head, tail equals 1, 2, 3, right? Head, tail, head is 1 and tail is 2, 3. But if we do head and tail of an empty array, head is undefined and tail is an empty array, which is what we want, right? We want tail, we don't want it to explode. We want tail to be the empty array because that's what it is. We want head to be, well, it's undefined. You know, there isn't a head. So that's why we're testing for undefined head. Then what we want to do, well, what do we want to do? We want to return whatever is the current value of the accumulator. Don't forget, the whole idea of reduce is we're sort of iterating over the elements of an array, right? And we're starting with a given value for the accumulator, and we're changing that accumulator value each time. So when we hit bottom, it's whatever the accumulator is, right? So let's return the accumulator. Otherwise, and this is where we start to get recursive. Otherwise, we call ourselves, but we don't call ourselves with exactly the same arguments that we've got, right? We call ourselves with the same function argument because we're going to pass that reducer function back into ourselves, right? But at this stage, we want to do the equivalent of, modifying the accumulator to be the new value according to calling that reducer function with whatever the accumulator is right now and whatever element we're currently processing, which is going to be head. And what do we call that on? Okay, we're calling the reduce function on the new accumulator, as in the evaluation of that. If we were to say, well, call it on the whole array, then of course, we'd never get smaller. The thing would never reduce. We'd never go over all the elements. We go head, 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 same thing, same thing, same thing, same thing. But of course, we've already set ourselves up for success in this area because we're going to say, well, call ourselves with the new value of the accumulator, but just passing the rest, as in the tail, because we've already processed head. I think that should be it, right? There's that fly again. It's flown out. Will this work? Let's see. Reduce. Well, I've still got the add function? Yes, okay. Well, let's try that. Reduce. Let's just make sure we got that reduce function, the new definition. Reduce. Yep, it's our recursive definition. In fact, this is the same call as we made last time, but with the other reduced definition. 21. 1 plus 2 plus 3 is 6 plus 4 is 10 plus 5 is 15 plus 6 is 21. It works. It only works. So I think we've done it already, haven't we? So does that make sense? Let me know in the chat right now. Does that make sense? We've got a reduce function defined similarly to what we had before, as in it takes exactly the same signature. It takes a function, it takes a starting value for the accumulator, and it takes an array, which we are in that very moment destructuring into the... Ooh. Ah, that's right. When you click on some code in the console, it opens up. That's what we found out last week, isn't it? It's like Inception, but in JavaScript. Jodel, I think I might have to quote that on Twitter. That is awesome. Yes, that is awesome. Hey, Ronnie. I didn't know you're on. Welcome and good morning. Good morning, Ronnie. Nice to see you. Yes, it's like Inception, but in JavaScript. Somebody put that on Twitter now, and I'll retweet it in a bit. That's awesome. Ooh, good logo there with the glasses. Logo emoji. I sort of understand what that emoji is. Anyway, that's another story. So where are we? So let's go back to the console. There we go. So we're destructuring the array into the first element and the rest of the elements using the rest operator. We've got our base case. Basically, if there's no head, then return whatever's the accumulator right now. Bang, done. Otherwise, we're going to return whatever the result is of calling reduce, or calling ourselves with a new value for the accumulator, which is the result of the evaluation of the reducer function combined with the existing value of the accumulator and the head element, the element that we're processing, but calling that on the array minus the head, as in the tail. I suppose we could write that, if we really wanted to, we could write that, if you were really crazy, like me, I suppose, fn accumulator head, I almost typed rest again, rest tail, head equals undefined accumulator, otherwise it's reduce fn, calling fn with the accumulator and head, tail. That's it. There's a single line definition. Does that still work? Yes, it does. Reduce. Let's just use multiply instead. Reduce x. Ax a times x, starting at 1 because the base value for a multiplier is 1. Nums. Yeah. Wow. Okay. In fact, take just the first 5 of nums. 120. 1 times 2 times 3 times 4 times 5. They were using our take. Good morning, Balaji. Good morning. Good morning. Nice to see you. Nice to see you. So I guess that's it. Oh yes, no, that's not it. We've got 10 minutes. Let's just pick one more function. Last Friday we were looking at some of the related functions, as in some of the let's call them methods, because they are methods from a JavaScript perspective. Okay. That we could implement using reduce, and let's implement it now using our recursive reduce. Not that it'll make any difference whether it's defined recursively or defined iteratively, because of course reduce has now become a building block. Includes. This is sort of includes. The includes method determines whether an array includes a certain value amongst its entries, returning true or false as appropriate. Now again, similar to one of the things we did last week, we can implement this using reduce. It won't be a very efficient one, especially if the arrays are long, because we're going to process every single one. And of course, if we find the thing that we're looking for right at the start of the array, then we might as well say, yeah, stop. Let's stop processing the rest of the array because we've found it. We can return true. But anyway, a factorial function. So Andrew, what were you referring to there? A factorial function? Was it something I said? Was it something I said? Okay, so why don't we try to implement includes? So yeah, we can see here array.1 includes 2. Yes. Cat, dog, bat. Array.pets includes cat. Yes. Pets includes at. Strange example value. Why don't I say banana or something, or some other animal that's not in there? False. Anyway, okay, so well, let's take that. Okay, let's have pets. Let's just grab that. Pets, cat, dog, bat. Now, includes. Is that what we want to do? Yeah. Okay. Includes. Takes. Again, this is the more standard way of defining a function, right? So just take. Here's all the arguments. Includes, and this is the thing we're searching for. So let's say val. An array, right? Notice it. Does anybody know why I'm defining the array always as the last argument in any of these function definitions that I've been defining with you? I'll say that again. Does anybody need to figure out what advantage having the array parameter at the end as the last argument in a function definition? In what circumstance might that be super advantageous? Let me know in the chat right now what you think. So we're going to implement this with reduce, I think. Reduce something. Now this is where this is confusing now. So obviously ... in this sense means something. Okay. Why don't I say oh, it's error. No, say something like that. Something, right? The starting value, as in the accumulator, is going to be something, and then we're going to process the array, right? Okay, so that's our sort of general framework for the definition. Includes returns a Boolean value. So why don't we start out with false? Just get the feeling it's going to be false. It's going to be easier, right? So we'll say basically glass half empty. It's not in there. Val is not a value that's in the array. But we can say evaluate the accumulator, or this is a bit like what was the other thing we defined last week? Sum. Anyway, does the here we go. So basically, does x equal val? That's it. I think that's it, right? So first of all, right, if we specify dog as the thing we're looking for, where's my mouse there? The first call to the reducer is a is false, x is going to be cat, and val is dog. And notice that here, and I don't think I mentioned this last week, one of the beautiful things about this definition is that it's using the power of a closure. Okay, this val here, and the array actually, is closed over in this function definition here. So we've got access to the val value, right? Nobody's put anything in the chat. Maybe I should leave that, and if you have to think about it and put it in the, if the stream ends, once the stream ends, put it in the comment. Have a think about why the array is best to define as the last argument in the signature. I'll give you a clue. There's a brilliant talk by Dr. Boolean, whose name escapes me. Oh, what's Dr. Boolean's real name? Brian Lonsdorf. There's a brilliant talk, which I've mentioned before actually, by Brian Lonsdorf, that explains why. Okay. Anyway, let's carry on. I think that's it, right? So if we say includes dog, so you see the way that the Chrome Developer Tool sort of uses double quotes, where I've used a single. Anyway, includes dog, pets, true. Includes rat, pets, false. Christian, trying to keep it with your thought processes. You and me both. Yes, I'm trying to keep up with my thought processes. I hope it's okay. So yeah, okay. Well, have a think about that, right? Okay, Jodel, you're with Christian on that one. Okay, so okay, you can always tell me to, explain more or slow down or speed up or talk slower. I can certainly type slower. So there we go. We got includes. We got includes as a function that we've defined using our reduce function. This time we're using the recursive reduce. We've defined our own includes. Again, reduce is this wonderful building block. It's like so powerful. It's like this fundamental thing. It's like an element like oxygen or hydrogen. Reduce. Right? 8:58. Okay, no time for any more. Let's finish there. Not related to your question, we can extend the includes to handle deep arrays. Oh, yeah, we could do. Yes, we could do. That would be really cool, wouldn't it? That would be a good way of extending our use of recursion, maybe. Okay, thank you all for staying with me. Thank you all for joining. Includes to yes, exactly. I like Samuele. I like the way that you've also defined you're using your chow array at the end, right? Yes, thank you for joining. Have a wonderful Friday. Have a wonderful weekend, and I'll see you next time. Bye for now.